The orifice plate and the venturi are similar devices that speed up the flow of the liquid through a constriction. The faster velocity through the constriction causes an increase in kinetic energy in the system. Having an increase in one form of energy means that some other form of energy has to decrease, and the energy that decreases is the pressure energy in order to make up for the increase in the kinetic energy. As the pressure decreases, then a pressure difference between the point of the constricted flow and a position before the constriction in the full bore of the pipe can be measured. This diagram illustrates that point using a manometer with a height difference of h shown on the venturi at the bottom. The other aspect of this diagram is the recovery of the pressure after the constriction. In the orifice plate, the recovery is only something like 70% because of all the turbulence that can be seen marked in yellow on the orifice plate diagram. With the venturi, the geometry of the venturi helps the energy recovery because those turbulences can't start, they don't occur. So up to say 96% energy recovery is possible with the venturi. There is a little bit of energy loss with the orifice plate as the flow shrinks down to get through the point of the narrowest flow. That's shown in green in the top orifice plate diagram. There's not a lot of turbulence there. Most of the turbulence and most of the pressure loss is in the yellow illustrated section, where the flow is in fact beginning to expand again. And that is the sort of shape of the venturi. The venturi in fact has a fairly short lead-in section and a fairly long lead-out section, which isn't illustrated very well in the lower diagram. If we just look at the venturi to develop the equation, it's the same equation for the orifice plate. But taking the venturi, we have the flow constricted down to its narrowest point, and that's marked as having an area A2. The flow approaching the constriction in the full bore of the pipe is shown as having an area A1. That's internal areas A1 and A2. And the pressure difference between those two positions in the pipe is measured as that height marked on the manometer there. Well, we have our two famous equations here in fluid mechanics. The continuity equation at the top there, which says that what flow goes in comes out, A1 U1 equals A2 U2, so A's area and U's velocity. So the two of them together are meters cubed per second flow through position 1 and meters cubed per second flow through position 2. And then the equation at the bottom there is Bernoulli's equation in terms of energy per unit weight, because we've divided through by G. In fact, that equates to simply measuring terms in terms of their head. So we have the first term is the pressure head, the second term is the velocity head, clearly fairly similar to half mv squared, or half times velocity squared. The third term on the left is the height above the datum, and then on the right hand side we have again the pressure head, the velocity head, and then the potential head. What we're about to do is to set our datum as being horizontal. Potential head terms Z1 and Z2, because we've set the datum horizontally, so they're both equal to 0. We can use our continuity expression, rearrange it for the velocity at position 1, that's before we hit the constriction, and by doing that, that enables us to substitute in for the initial velocity u1 the expression a2 over a1 times by u2, So now we have an expression where the only velocity in the equation will be u2. While we've rearranged the equation here, having taken pressure over to the right hand side and velocity is all on the left hand side, we've made our substitution removing u1, having used continuity. So on the left hand side all we have is velocity in terms of u2, the velocity at the constriction. And now we've rearranged the equation so that having obtained the velocity u2 on the left hand side, if we multiply it by the area, then that gives us the total volumetric flow rate. So Q in meters cubed per second is equal to A2 times by U2. And of course it's the same flow rate at position 1 as position 2. That's our continuity equation again, that what goes in comes out. On the right hand side of the equation, apart from the rearrangement, we've also added a discharge coefficient, illustrated here as being capital C, sometimes CD. And that really is something to take into account some of the energy losses in our system. So for an orifice plate that might be 0.6, 0.7, whereas in a venturi maybe 0.9, 0.96, something of that sort of order. Of course we can now substitute in for P1 minus P2, the pressure difference, and we can substitute in the equation depth times density, the static head equation. If we do that, we can then cancel the density terms out, but that sort of hides a secret, because if we do that, bearing in mind the density in the square brackets has come from Bernoulli's equation, that's the density of the process fluid, the fluid flowing through the venturi or the orifice plate. So really if we do that, that gives us the pressure measured as a height of process fluid, normally liquid, flowing through the system, which is kind of a difficult concept, because that means we're measuring the manometer height, h in the diagram, in terms of height of the liquid that's flowing through the system. Of course you wouldn't have an interface there, so if you like, if you do that substitution, it's a kind of an imaginary height of liquid in a manometer, whereas in reality you might, for example, be using mercury to measure the pressure difference of the process fluid water. So the height will be different because mercury has a much higher density than water. It's probably safest to leave it as P1 minus P2 and not to make that substitution unless you really know what you're doing. So the last thing to consider is this discharge coefficient, which its name gives it away really. It's a coefficient, it's not a constant, and that coefficient depends on the Reynolds number through the orifice and also the design. So we can have a chart, and you can see here that for Reynolds numbers really above 100 and through 1,000 to 10,000, we're typically looking at a discharge coefficient of 0.6 to 0.7-ish for this particular orifice plate. We'll change a little bit with the design of the orifice plate, maybe even getting as high as 0.9, but a typical value is 0.6 to 0.7. It's not all flow measurement. This is kind of a neat idea. Instead of using a venturi for flow measurement, this is a big venturi, and it sits inside a river. And the idea here is the low pressure at the throat of the venturi causes air to be sucked in from a tube that goes above the surface of the river, and that air being sucked in drives a turbine, so it generates energy from the flow of the river. Of course it also aerates the river as well, but that's kind of useful because you're putting oxygen into the water. So it's a nice little spin-out company making some money with renewable energy.